Preparation. Let us see. Who is going to present first?
I
Nandana?
am. Yes, sir.
Okay, welcome Nandana. Please come on to the stage. Come on, begin. Best of luck.
Thank you.
Yes, begin.
A very good afternoon to everyone present here. I am going to be teaching a little portion from the second chapter, Atomic Models. So right before I begin the atomic model portion, I would like to do a little quick recap on subatomic particles of an atom. So there are three subatomic particles in an atom, namely protons, electrons, and neutrons. Protons, they are the positively charged particles in an atom, and they were first discovered by Ernest Rutherford in the early 1900s. So it has a charge of +1. Next, we have electrons. They are the negatively charged particles in an atom, and they were discovered by J.J. Thomson in 1897. Now we have neutrons. They are the subatomic particles with no charge. That's why they are called neutrons. And they were discovered by a scientist named Chadwick in 1932. These are the subatomic particles. Now, before I go to the details of both the atomic models that I'm going to teach, that is J.J. Thomson's model and Rutherford's model, I want to explain a little bit about why atomic models are necessary. So, in Dalton's atomic theory, it was explained that atoms are indivisible particles. But this was disproved by many other scientists during their experimentations. So the next thing that it was important to explain the features of these subatomic particles and their distribution and their contributions in an atom. That is why atomic models were necessary. So first we have J.J. Thomson's model of an atom. After a lot of experimentation, he proposed in 1898 that an atom possesses a spherical shape. He further suggested that the positive charge is uniformly distributed, which means the whole spherical cloud. Here there is a picture. The whole spherical cloud here you can see is positively charged, and the electrons are embedded on them in a scattered manner. The next point he said that we have is the names. There are various names given to this model, like plum pudding model, watermelon model, etc., due to its physical resemblance. One of the other most important aspects of this model was the mass. The mass of the atom he assumed to be uniformly distributed all over the atom. Here I have put two pictures which explains the atom, the model of the atom, and why it is called watermelon model and plum pudding. In the watermelon model, you can see the red flesh of the watermelon is what symbolizes the positive cloud, and the electrons are symbolized by the seed, the black seed. Similarly, in the plum pudding model, the whole pudding is spherical, the positive charge, and the corpuscles of electrons are symbolized by the small pieces of fruit. Next, we have Rutherford's nuclear model. Here, the picture that I have shown here is the experiment that he conducted to form his model of an atom. So he believed, according to Thomson's model, he had conducted this experiment, and there were a lot of people who disproved the J.J. Thomson's model of an atom. Due to this, he figured an experiment which could make his new model of an atom. This is also known as alpha particle scattering experiment. So what he did was he took alpha particle rays. He took these alpha particles, kept them in a lead box, and then let it bombard on a gold foil. On the bombardation of this gold foil, when the alpha particles would bombard on the gold foil, he expected the results to be non-deflected particles hitting the screen. The screen would do nothing, but it would glow. It was a fluorescent screen. So when alpha particles would hit the screen would glow, showing the presence of alpha particles. So let's just go through the points again. A stream of high energy alpha particles from a radioactive element was directed at a thin gold of foil. Thickness was around 100 nanometer, which means it was very thin. Only 1000 atoms was there of gold. In order to study the deflection caused to the alpha particles, he placed this fluorescent zinc sulfide screen around the thin gold foil. Now, this is a little extra information I've put here. Gold foil. Why did he use gold foil? He used gold foil because it's an extremely malleable metal, and he desired for a thin layer of gold foil for his experiment to be taken easily. Now we see the expected results and the actual results. The expected results were on the basis of Thomson's model, and the actual results were on the basis of Rutherford's model, how he found his model. So Thomson's model, according to his model, he expected all of these um, alpha particles to go straight without any deflection because the mass was uniformly distributed and alpha particles have high energy. So they can pass through these atoms without any deflection. The only little deflection that would have been shown was due to the slowing down of these alpha particles from air to a denser medium. However, this is not the result that he found. He got these different results than what was expected. The first result was most of the alpha particles passed without any deflection. The second result was as it came close to a little mass, a denser mass, it deflected with small angles, a small fraction of alpha particles. And the next one was that like around only 1 out of 20,000 alpha particles, that was the approximate number, those many alpha particles rebounded, which means they deflected back at 180 degrees. So these were the results found. So according to these results, he concluded the following. First, he suggested that most of the space in the atom is empty, which means all of these, you see here, this is the atom, this is the positive mass that he expected, that he found in his nuclear atom. All of the space, he said, was empty because there was no much deflection found. The next point, for the particles to be deflected back, the positive charge of the atom needs to be concentrated in a very small volume. So as I said, there was small amount of alpha particles that deflected in small angles. For this to happen, there should be repulsion between the two like charges. Alpha particles are positive, so was the mass in between, in the center. Due to this, deflection took place. Due to the repulsion, the deflection took place. His further calculations showed that the volume of the positive mass is negligibly small as compared to the atom as a whole. So here you see the whole atom, these dotted dots, these dotted circles, and this is the central positive charge mass that he found in his nuclear atom, in his model. So this is extremely small as compared to the whole atom. That is, these are his conclusions. Now we'll see what he actually said about his atom. So this is a Rutherford's model of an atom here. The positive charge and most of the mass of the atom was densely concentrated in a region, in the central region here you can see. This is a positive mass that he said he called this a nucleus. The nucleus is surrounded by electrons that move around in circular paths called orbits. You see these orbits here, and there are these small electrons revolving around them. They revolve around in high speed with high acceleration. The next one is the electrons and the nucleus are held together by electrostatic forces of attraction, which means the nucleus is positively charged and the electrons are negatively charged. We know that like charges uh, repel and unlike charges attract. So due to them being unlike charges, there is an electrostatic force of attraction which keeps them together. Now, this is also called the planetary model of an atom. Why? Because his model resembles the solar system. We know about the solar system. So the sun is in the center and many planets revolve around the sun. So here, if you see, there is a resemblance. The nucleus is symbolizes the sun in the solar system, and the electrons revolving around in these orbits represent the planets. This is why it is called the planetary model of an atom. Yeah. So I hope everyone has got what I have taught right now. I hope everything is clear. Is it clear?
Yes.
Yes.
Okay. So I'd like to ask some questions since I've explained a little bit. What are subatomic particles? So I did a little quick recap of subatomic particles and what they are. There are three subatomic particles. Now, what are they? Atul?
There are protons which are positively charged, neutrons which have no charge, and electrons which are negatively charged.
And let's ask Achal. So I explained why atomic models are necessary, why atomic models are presented. If you can recollect, could you just explain?
Because earlier we never knew there was a nucleus.
Is that the point?
Yeah.
I doubt. That's not what I explained. Okay, let me ask someone else. Punya, could you help him?
It was assumed that atom cannot be further divided into other particles.
Yeah, and then due to the presence of subatomic particles, there was
It
a
was
need.
to explain how
Yeah.
they were.
Yes. Thank you. Then, okay, Achal, an easier question. J.J. Thomson's model. What is it? How is it presented? Any 2 points. Just 2 points.
It resembled like solar system. Is it that?
J.J. Thomson.
Thomson's model. Thomson's model.
Or plum pudding.
Yeah. So tell me the postulates.
Yeah, in the plum pudding model, the uh, no, like electrons, these things were equally equally distributed.
Electrons are equally distributed.
No, the charge was equally distributed.
Okay. You're partially correct.
Just that.
Okay. Nevin, can you help him?
What do I need to say?
The J.J. Thomson's model. What did I say about the positive charge and the negative charge?
In relation with the plum pudding thing?
Yes. Okay, no
The fruit,
idea.
the fruits are the electrons, and the pudding thing is the positive charge.
Yeah.
They are embedded inside the positive.
Yeah. Okay. Thanks.
So can we expect any free space in the atom in the Thomson's model, maybe? Can we expect a free space?
In here.
You could not hear?
My volume was mute.
Can we expect a free space in the Thomson's atom model? The plum pudding model? There is no free space. There is no free space. I call it as the Ledoux model of atom, Ledoux model. Yes, Ledoux model. The yellow colored bundi maida, that is the positive charge, positive sphere, and the plum. And that is the electron space. Okay, carry on, Nandana.
Okay. Rutherford's model. Is anyone voluntarily ready to explain the Rutherford's model? Just 1 point.
Come
Anyone?
on.
No.
Hey, come on, please.
Okay, then I'll call out someone. Krishna Chandra. Are you there?
Krishna, please come.
Oh, he's not there.
Krishna's gone.
Yes. Evelyn.
Only 2 minutes more.
How about Atul?
Finish. Okay.
Yes, sir.
So before we pass on to the next presenter, let me say 2 words about the Rutherford atom model. That is the, as Nandana told, it is the solar model of atom, or it is the planetary model of atom. And it has got a largest free space also. Since there is nucleus, it is called the nuclear model of atom. It's called, Rutherford's model is called the nuclear model of atom also. See, Nandana told that there is attraction between the nucleus and electron. Nucleus is positively charged, electron is negatively charged. Normally, there is attraction between the nucleus and the electron. That is why the electrons are held in the atom. That is what Nandana told. That is right. If there is attraction between nucleus and electron, what will happen to the stability of the model? Will it be stable? Will it be the solar model? Will it remain there? There is attraction between them, and due to attraction, what happens? Nucleus is a massive particle, as you told. It's a massive particle. Electron is a massless particle. It's very, very, very minute mass, massless particle. So due to the attraction, what happens? Electron will be attracted towards the nucleus. Is it not?
Yes, sir.
Nucleus is the heavier particle and electron is a massless particle, we can say. So if there is attraction between these two particles, normally what will happen? The electron will be attracted towards the nucleus and it falls into the nucleus. It hits the nucleus. There is a chance for that. And the system collapses. The system is not stable. Do you agree with me, Nandana?
Yes, sir.
Okay. So that is one of the limitations of Rutherford's model of atom. There is a chance for the attraction and the moving of the electrons towards the nucleus. And it will be falling into the nucleus. The electron hits the nucleus and the stability of the atom is collapsed. And that is one of the limitations. And then Rutherford gave another explanation. And that is the centrifugal force. The attraction between the nucleus and the electron, that is the centripetal force. Centripetal force. That is feeling, that is experiencing towards the nucleus. Am I right? That attracting force is mainly, that is towards the center of the atom, towards the nucleus. And when the electron revolves around the nucleus, due to the revolution of electron, rotation of electron, a force is gained by the electron. And that is called centrifugal force. So the force attained by the rotation, the centrifugation, the rotation, the revolution, that's called the centrifugal force. The centrifugal force is acting outwards. That is acting outwards. While the centripetal force, that is the attractive force, that is acting towards the nucleus. And these two forces are equal but opposite. And therefore, there is no collapse of the structure. That was Rutherford's argument. Right? Okay. And regarding these portions, these are not included in the syllabus, but these are the preliminary portions. It is good to know. And you have done well, your presentation and say the PPT and all these things. You have done well. Congratulations. Now, Gayatri, please come on to the stage.
Good afternoon to you all. Today, I'm going to present something from the first chapter. Wait a sec.
Come on.
Um, you can see the screen, right?
Yes. Today, we are going to learn something about atomic and molecular masses. So, before going into atomic and molecular masses, let's go to learn just briefly about what is atom and molecule. You know, in the 19th century, scientist Berzelius, he, um, he came up with the hypothesis under which it says that under similar conditions of temperature and pressure, equal volume of gases contain equal number of atoms. But for that to be true, we have to take half of hydrogen and half of fluorine to get one HCl. And if we do that, we'd be going against Dalton, who said that atoms are indivisible. So another scientist, Avogadro, came up with two terms, atoms and molecules. He said that atoms are the smallest substance and it may or may not have independent existence. On the other hand, molecules are something which are made up of two or more atoms. Now, let's see what is atomic mass. See, atoms are really small, hence atomic masses are very, very small. And today we have many sophisticated techniques to fairly calculate atomic masses. And one such technique is mass spectrometry. But earlier, scientists determined the mass of an atom relative to another by experimental means. They use hydrogen, it being it the lightest atom, and they gave it an atomic mass of 1 without any units. And they use it as a relative. But in the present system of atomic masses is based on carbon-12 as the standard, and it has been agreed upon 1961. And what is this carbon-12? It's nothing but carbon-12 is one of the isotopes of carbon, and it is represented as carbon-12. Now, in this system, carbon-12 is assigned the mass of exactly 12 atomic mass units. And let's define one atomic mass unit. One atomic mass unit is defined as a mass exactly equal to 1/10 of the mass of one carbon-12 atom. And it's given as 1 AMU is equal to 1.66056 into 10 raised to negative 24 gram. Now let's see the atomic mass of hydrogen. We know that mass of an atom of hydrogen is 1.6736 into 10 raised to negative 24 gram. So the mass in terms of AMU, that is the mass of hydrogen atom, is mass of an atom of hydrogen divided by mass of one AMU, which is 1.008 AMU. And this we can use this to find atomic mass of all other elements. Like the mass of oxygen is 15.995 AMU. And at present, we don't use the term AMU, and it has been replaced by U, which stands for unified mass. Now, let's see, what is gram atomic mass? It's really simple. Gram atomic mass is just the mass in terms of gram. And how do we find them? It's nothing, but you just have to change the U to G. That's it. Now, let's see what is average atomic mass. For the naturally occurring elements, exists as more than one isotope, right? So how can we find their average atomic mass? For this, we have to take care of two things, that is, existence of these isotopes and their relative abundance. And again, what is relative abundance? is nothing but the percentage of its occurrence in the nature. Now let's take an example of, let's take carbon as an example. We know that carbon has three isotopes, that is carbon 12, carbon 13 and carbon 14. And in this table, it's given their relative abundance as well as their atomic mass. And how can we find their average atomic mass? You just have to multiply their relative abundance and atomic mass and just add it up, which is 12.011 U. Pretty simple, right? Now, there is a fact, just something really interesting. In our periodic table, the atomic mass which are mentioned is actually is their average atomic mass. Okay. Now let's see what is molecular mass. We have said earlier that molecule is when two or more atoms come together, right? So molecular mass is mass of one molecule. Now let's see the definition. Molecular mass is mass of an atom, is mass sum of atomic masses of the elements present in the molecule. Now let's take an example let's take the example of molecular mass of methane. We know that atomic mass of carbon is 12.011 U plus 4 times the atomic mass of hydrogen, because there are 4 hydrogen atoms in the one molecule of methane. So the molecular mass of methane is 16.043 U. Now let's take another example of water. H2O is equal to 2 times the mass of hydrogen and 1 times the mass of oxygen, which is 18.02 U. Now let's see what is gram molecular mass. It's very similar to that with a gram atomic mass. It's just that the molecular mass in terms of gram. And how do we find them? Just change the unit to G, like we did in the gram atomic mass. Now this is something interesting, formula mass. Let's see. In some substances like sodium chloride do not contain discrete molecules as their constant units. Like you can see the structure on the right hand side. It's just like a cage or a three-dimensional structure. In this, one sodium ion is connected to 6 other chlorine ions. And how do we find their mass? Is it possible that we use the molecular mass? No, it's not very practical. So what we do is we find the formula mass. And how do we find them? We just use the atomic mass of sodium plus atomic mass of chlorine, which is 58.5 U. Now let's see the formula mass of glucose. It's 6 times the formula mass of carbon plus 12 times the atomic mass of hydrogen and 6 times the atomic mass of oxygen, and which is 180.162 U. And do you have any doubts? Any doubts? Then I'll ask some questions. Punya, can you please define one atomic mass unit?
1/12 the mass of carbon 12 atom.
Yeah, correct. And can anyone say what is molecular mass? Achyut? Nandana?
Mass of one molecule of any element. The
Correct.
molecular mass.
Do you guys have any doubts? Thank you.
So Gayatri, you have done well. Your presentation is very good. And I would like to add say some more points regarding the molecular mass. Yes, Gayatri told that molecular mass is the mass of a molecule. It is the mass of a molecule, you told. That is right. But it is not the exact mass. You said it is the sum of the atomic masses. That is also correct. But we can define molecular mass in another way also. As we have done, atomic mass as a relative mass. A relative mass. Molecular mass also is considered as a relative mass. That is relative to 1/12 of a carbon 12 isotope. Here also the standard taken. The standard taken is carbon 12. The unit taken is 1/12 of a carbon 12. No doubt. Okay. So molecular mass is the ratio of the mass of a molecule to 1/12 of a carbon 12 isotope. Just like atomic mass. Atomic mass is equal to mass of an atom by 1/12 of a carbon 12 isotope. Similarly, molecular mass is equal to mass of a molecule by 1/12 of a carbon 12 isotope. That is why we replace the AMU, atomic mass unit, by unified mass U. If a unified mass U is used, that is applicable for both atomic mass as well as molecular mass. Okay. Atomic mass unit, AMU, atomic mass unit. If we use that term always, that is better applicable in the case of the atomic masses. But if you replace it by U, unified mass U, it is also 1/12 of a carbon 12 isotope. Now you can compare. So the term unified mass U is taken. As you said, it is the sum of the atomic masses of the various atoms present in a molecule. No doubt in that. But we can define that in another way also as a relative mass. That is mass of a molecule by 1/12 of a carbon 12 isotope. So much U, unified mass. So unified mass, that unit can be used for both atomic masses and molecular masses. That's why we replaced atomic mass unit by unified mass U. Okay. So you are done well. See, there is a saying. It is like this. Child is the father of man. This is not my words, my quotation. This is given by Wordsworth, William Wordsworth. William Wordsworth, the famous poet, English poet, he says, child is the father of man. Why? Because we are to learn a lot of lessons, a lot of things from the children, from their innocence, from their openness, from their sharing experience, from all these things. We have to learn a lot of things from the children. Similarly, the so-called teachers like us, or like me at least, have to learn a lot of things from you people. And you have done better than I do in my class. You have taken very good presentation, PowerPoint, very tables, everything you have taken. You have prepared well. So you can become very good teachers, very good instructors. Not simply very good presenters. You can become very good teachers and very good instructors also. So I congratulate all of you, not only the presenters, but also the listeners, including me. Okay. So let us congratulate the presenters, Nandana and Gayatri. Give them a clap. Come on. Okay. So keep up all these things. It is time to wind up. So let us stop now. Let us meet again the next day. Thank you.